Hello, and welcome to this video on Introduction to Soldering and Brazing. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to use. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com. Today, we're going to look at soldering and brazing. It's one of the metallurgical joining techniques that are commonly used in manufacturing. Here, I'm showing you a solder connection between two components, and you can see the solder joint over here between the two. And you can also see a solder fillet on the external edge of the solder. The gap between the two components in this case is about 2 thousandths, so 50 microns. Soldering and brazing are joining processes used to form a metallurgical connection between the two components by adding a filler metal that melts and bonds to both without melting the base components. So the main thing to realize for soldering and brazing, it's a metallurgical connection. So it's not a mechanical connection like nuts and bolts. So it is form a metallurgical bond between the two components that you're trying to join. At the same time, these processes occur at a low enough temperature that the base metals themselves do not become soft or melt. So they are not participating in the process in that sense. There are some reactions between the solder or braze alloy and the base metal components, but the components themselves don't melt. Solder and braze can be strong. One of the misunderstandings about soldering and brazing that the joints are weak. While solder and braze being a low temperature, solder being obviously less temperature melting point than braze, are fairly soft compared to welding. But they are soft on a unit basis. With the right design of the components, if you make the braze or solder of a sufficient area, then the joints can be fairly strong. Solder joints can be quite easily be made to be hermetic, that is leak-proof. They are electrically conductive, and they can also be actually fairly visually appealing, as you can see from the solder fillet on the edge over here. It forms a nice round fillet and actually looks quite pretty. One of the unique aspects of soldering and brazing is this phenomena called wetting. Wetting is a phenomena where the braze or solder alloy will melt and flow into the gaps to form this joint. Now, what exactly is wetting? Let's look at that on the next slide. Here I'm showing you two schematics. One on the left, it says good wetting, and one on the right, which says poor wetting. Here I'm showing you two components. They're shown reddish in color, kind of implying they are made of copper, but doesn't have to be copper. And we're showing a molten solder droplet sitting on the top of one component, on both components. And the shape of that droplet is different. When you have good wetting, the droplet kind of spreads, and the contact angle at the edge of the molten metal is less than 90 degrees. When you have poor wetting, the contact angle on the edge of that droplet is going to be greater than 90 degrees. So wetting is the process where the braze alloy melts, flows, and as it forms that angle, the angle is less than 90 degrees. That is the key definition of wetting. Now, what exactly or how do you control wetting? The wetting depends on cleanliness of the component surface. So when the metal surface is clean, as in clean of contamination or does not have oxides, then there is a greater chance that the braze alloy or a solder alloy will actually wet. Now, that cleanliness can be achieved by adding a flux. So flux is a chemical used for reducing these oxides, and we'll talk about that in a later slide. The second factor is the affinity between the braze and the component surface. So you have to use the right solder composition to encourage that affinity between the solder or the braze and the base metal. And the third is the viscosity of the molten metal. and that depends on temperature and composition. So if that molten solder is very viscous, then the contact angle will be less. If the molten solder or braze is very fluid, then the contact angle will be less. So even within that less than 90 degrees, there can be better wetting or poorer wetting. And there's a good reason to actually select one of the two, and we'll discuss that in the next slide. So what exactly is the effect of wetting? So wetting produces what is called a capillary action. So capillary action is a process where when you have a capillary is any tube of a very, very small diameter. Let's say you have a beaker of water and you have a very, very small tube, and the tube has good wetting for water. And if you insert that tube into that liquid, the water, even against gravity, can actually go up into the tube, and the level of water in the tube will be higher than the level in the beaker. And that is produced by capillary action, and that depends on wetting. So here I'm showing you two schematics, again, similar to the solder connection that I showed you before. And here I'm showing you again the angle. The contact angle over here is less than 90 degrees. On the right-hand side schematic, I'm showing a contact angle which is more than 90 degrees. If the alloy has poor wetting and the angle is more than 90 degrees, then it will be reluctant to go into the gaps. So when you make a solder joint or a braze joint, you place the braze alloy or the solder alloy outside the joint or right next to that opening in the joint. And during the brazing or soldering process, you expect the braze alloy to melt and then flow into that joint. And that flow happens when the angle is less than 90 degrees. If the angle is more than 90 degrees, it's not going to flow into these gaps. If the angle is less than 90 degrees, it will flow into the gaps. However, how big the gap it can flow into, that will still depend on the viscosity of the melt at the operating temperature. If the alloy is very viscous, then it won't fill into small gaps, but it will fill bigger gaps. So sometimes that's a requirement. Sometimes the fit up is such that the gaps are big and you want a more viscous alloy. Sometimes you want the gaps to be filled are very, very narrow. And in that case, you want a very, very low viscosity alloy, which is very liquid and just rushes into that gap. And that is by capillary action. So how do you control the viscosity of the solder or braze? Let's look at a tin lead eutectic phase diagram. So this is a phase diagram I'm showing over here. On the vertical axis is temperature in degrees centigrade, both on the left and the right axis. On the left is pure lead. So this axis corresponds to pure lead. So if you take lead and start heating it up, it's going to be solid up to 327.5 and then it becomes liquid. Same on the other side, if you start with 100% tin and heat it up, it's going to go up to 232 and then become liquid. However, the mixture produces an interesting result. So here we can see that what is called the liquidus, where liquidus is the line above which all mixtures are going to be liquid. So the liquidus line drops from 327 down to 183 degrees centigrade. And then after certain addition of the ratio of tin, the temperature again starts going up to the melting point of tin. So the horizontal axis over here is showing a mixture of lead and tin. Of course, this is not a linear scale. That's why you see the spaces being not exactly the same. The unique combination of mixture where we have 61.9% tin and the remaining is solder has the lowest melting temperature in this system. So the mixture of 61.9 tin and the remaining solder melts at 183 degrees centigrade, just like a single element. So if you take a special solder, and you can buy these, you can buy a eutectic solder. and you raise the temperature from room temperature, go up to 183 degrees centigrade, and it's solid up to 183, then immediately becomes liquid. So even if you're slightly more than 183, it's going to be quite liquid and fluid. So this mixture, which is unique, that it has a lower melting point than both tin and lead, is called the eutectic. So eutectic is a Greek word for easily melted. That's where the word comes from, that a mixture which is easier to melt than the base metals. So eutectic is an alloy which has the lowest melting point, but it also, as soon as it melts, it becomes very liquid. So for some applications, that's a good combination. But sometimes you want a more of a pasty or more of a viscous fluid as the braze or a solder. So in this case, we're talking about soldering. So we can go to a 50-50 mix. So you can buy a 50-50 mix of tin and lead. And that has an interesting behavior. When you increase the temperature from room temperature up to 183 and you go slightly higher, you will find that only a small amount of that alloy starts melting. And as you go higher in temperature through this range called the pasty range, you will find that increasing amount of alloy becomes liquid. And once you go above the liquidus temperature, the entire alloy is fully liquid. So if you want to control the viscosity, then you can operate in this pasty range where the alloy is actually viscous. And you can control the viscosity by temperature, by composition, and that will define what small gaps this braze alloy or a solder alloy can get into. Now you will find that you must have heard of tin lead solders, but you will find that almost all the solder alloys which are used in this system are in this range. They are somewhere between 50-50 and eutectic. And you can buy many different compositions in between, and they each have slightly different behavior. Now, once the alloy melts, how does it react with these base metals? So let's look at that. Here I'm showing you a cross section of a solder bond where you have two components which have been joined, and you can see an intermetallic layer at the interface on both sides and a eutectic alloy which is filling the middle. So what happens is when you select a particular braze or solder composition, that only some of the constituents of that composition will react with the base metal. So for example, if you take a tin-based solder, let's say you take a tin lead solder. When the solder alloy melts and you have the right flux and you remove the oxides from the surface, the tin will then react with the base components. Now, the base components are typically in soldering is copper, or they might have a nickel plating or a gold plating on it. And tin will react with all of them to form intermetallics. And oftentimes the intermetallics will form a thin layer on the surface. A lot of times the layer is so thin that it is very difficult to see. So you might feel that in this case, there is no reaction product, but the reaction product is going to be there. It's going to be just very, very thin. These reaction products often do not include lead. So in case you're using a tin lead solder, the lead is only there to control the viscosity and the melting point. So the presence of lead is only used to control the viscosity and melting point, but not for reactions. The reactions are all between tin and the base components. However, lead is very poisonous. So now we have found out over the last many decades that lead is not good. So if you make components of tin lead solder and those go into the landfill, the lead leaches out and gets into the environment, and that's not a good thing. So a lot of rules have now come into place. Again, these rules have been there for quite some time, where for many applications, we are now using what is called lead-free solder. So what exactly is a lead-free solder? Obviously, as the name implies, there is no lead in this solder. So here I'm showing you a phase diagram. This is between silver and tin. So the left axis is temperature and silver. So If you start from the room temperature and heat it up, silver will melt at 961 degrees centigrade. On the right-hand side, the tin will melt at 232 degrees centigrade. In this system, there is also a eutectic. Now, this eutectic is very close to 100% tin. At about 96.5% tin, the eutectic will melt at 221 degrees centigrade, which is 10 degrees less than the melting point of tin. And what researchers have found that this alloy, SAC or SAC 305, which is 96.5% tin, 3% silver, and 0.5% copper, works quite well. And this is one of the probably the more popular alloys for lead-free solder. So good thing is there is no lead. However, there are some issues. First of all, the melting point of this solder is good 20-30 degrees higher than a tin lead solder, and that produces challenges. Secondly, the cost is also greater. Now we are adding silver and we are adding a third component. As the mixture becomes more complicated, the cost also goes up. And perhaps the most detrimental is what is called tin whiskers. So what exactly is a tin whisker? Now, tin whiskers do not form in tin lead solders. So this is one of the benefits of tin lead solders is we do not have the issue of tin whiskers. However, now that we are using lead-free solders, we have to deal with this phenomena called tin whisker. So what exactly is a tin whisker? As I'm showing you a photograph over here, where a tin whisker has grown. It's like a single crystal. It's almost like a needle. It grows from the solder surface. And if it grows in the direction of a neighboring electronic component, it's going to create a short and the device is rendered useless. So how do we try to reduce, what are the mechanisms by which we can try to reduce tin whisker formation? So one of the things is reduction of stress in the solder joints. Why would we have stress in the solder joint? The reason we have stress is we are making a solder joint at a certain temperature, and from there we cool it down. Now, when any metal cools down, it is going to have a certain amount of contraction. And how much it contracts depends on its coefficient of thermal expansion. When you look at a solder connection, it is actually quite complex. It has the FR4, let's say it's on a circuit board. We have the FR4 base, which has a different thermal expansion coefficient. The copper trace has a different CTE. The solder itself has a different CTE, and the electronic component, which often is made of a ceramic of sorts, will have a different CTE. So when all of these components are at a soldering temperature and then they cool down at different rates and different expansion coefficients, and the solder, even though it looks nice and clean, can have a lot of stress in that joint. So one of the things you have to do is to reduce the stress by more finesse and control of the cooling rate as it comes down to room temperature. The second is to use a nickel barrier layer. Turns out that if there's a copper migrates into the solder, there is a greater chance of tin whisker formation. So one of the things people have tried is to put a nickel barrier layer. And the third is to reduce flux residue in the solder area. So presence of flux or flux residue also seems to encourage tin whisker formation, which we don't want. So that is the debate in the sense that tin lead solders have some very good properties, very easy to use, low temperature, good flow, but lead is poisonous, so we cannot use lead. So many industries have moved away from lead-based solders and are using lead-free solders, but those have their own challenges. We only discussed the tin lead system or tin-based systems. There are other solder families such as based on bismuth or indium or gallium and so on. And they also sometimes have tin. So there are many, many different options. But the fundamentals of the eutectic melting and reactions, that doesn't change. Solder is an application where the melting point is below 450 degrees centigrade. And we have braze alloys, where the melting point is greater than 450 degrees centigrade. Now, where does this 450 come from? It is quite arbitrary. There is no real differentiation between soldering and brazing, but just by conventional logic, 450 has been used as a dividing line. Brazing is also similar. Brazing is as often is based on a eutectic phase diagram. So here I'm showing you a eutectic phase diagram between silver and copper. So here again, we have melting point on the vertical axis, and silver melting point is 961. Copper melting point on the right is 1084. And the mixture of silver and copper at 28.1% copper actually melts at a much lower temperature of 780 degrees centigrade. So you will find alloys based on a particular metal with additions of suitable composition. So this is the basis of the silver-based brazing alloys. So typically silver-based brazing alloys will have silver, copper, and in addition to that, they can have cadmium, zinc, and a whole bunch of other little things to control not only the melting point, but also the viscosity when the solder alloy melts. So here again, we have many choices. You can have, I think they're close to like 20 or 25 different types of silver-based braze alloys. And there are also similar families of aluminum-based braze alloys, copper-based, nickel, gold, and palladium. Oftentimes, when you're trying to braze something, the braze alloy is quite similar to the base metal. So if you're brazing, say, a nickel-based alloys, you're going to likely choose from nickel-based braze alloys. So if you're brazing Inconel, you're going to use a suitable nickel-based braze alloy. But that's not always the case. You can actually use copper-based braze alloys for brazing to stainless steel. So there are a lot of mix and matches which are available and possible out there. Most of the braze alloys, as I mentioned, and solder alloys are based on eutectics. That means you are using a mixture to reduce the temperature and then add a few other things. But that's not always the case. There's always an exception to the rule, and this is a good one. Here we have a resistance brazing application where we are brazing a Kovar lid. Now this lid is about, say, a millimeter thick over here to a Kovar electronic package. And both these components have gold plating on them. And this is pure gold. It's not a eutectic mixture. And the gold is already plated on there, so you're not adding it like a foil or a paste or anything. And because gold is clean, it doesn't even need a flux. So gold is very unique as a brazing alloy in that sense, and especially in this application. So it is plated, it is not a mixture, and it does not need flux. And you can see that this is a cross section where you can see the two parts have been joined over here. So the Kovar is not actually joining to Kovar. The gold is on either side is joining to each other. And some of the gold is getting squeezed out and forms a nice fillet on the outside. So this is a very unique brazing application. Resistance brazing, as in using a resistance welding equipment to generate the heat, is one of the ways of generating the heat. There are many other ways to generate the heat, and we have different sources. These are the commonly used sources for soldering. And over here, I have shown commonly used sources for brazing. Soldering being a low temperature, the most common soldering equipment for manual soldering is a soldering iron. So this is perhaps the most common or most familiar welding or metallurgical joining technique that people might have used in their daily life. A lot of people have done soldering when they're in high school or in their garage or for different jobs. So soldering iron is a very, very common, and you can easily buy a soldering iron and do soldering at your home as well. It is very safe and easy, although the flux has to be taken care of. Another common technique is hydrogen flame. Of course, hydrogen is a little bit risky, so it's more in a professional environment that you can use a small hydrogen flame torch to provide the heat. You can also have a solder pot where the solder is already molten, and you are actually taking the components to be joined and just dipping into the pot, and they're soldered. Wave soldering, reflow oven are perhaps the most common techniques in soldering for making circuit boards. Other techniques which are not as common but are industrially used is laser soldering. So you can do individual components on an electric circuit board by laser beam. You can do resistance soldering, similar to the resistance brazing I showed you before, and induction soldering, again, for small components, localized. Brazing heat sources are slightly different because you need to get to a much higher temperature. Brazing is more than 450. Oftentimes, it's actually close to between 800 to 1,000 degrees centigrade. There again, you can do manual brazing, so you can do torch brazing manually, but most of these are often done in a semi-automated or an automated method. We have furnace brazing, torch brazing, dip brazing. Dip brazing is similar to a solder pot where you're actually dipping the entire assembly into a molten flux. And the temperature of the flux does the cleaning job, also melts the braze alloy on the surface. This technique is commonly used for joining or making aluminum heat exchangers. Then you have vacuum oven brazing, laser brazing, resistance brazing, and induction brazing, which are very similar to soldering. Both soldering and brazing can be done as manual, semi-automated, as well as fully automated processes. Now, this slide itself is a separate discussion by itself. So at some point in time in the future, I'll be posting a video on getting into more detail on all of these processes. Another important aspect of the brazing process is the flux. It is very difficult to get metals to be completely clean both in terms of cleanliness and in terms of not having an oxide on the surface. You can get parts to be fairly clean, but they still have an oxide on the surface. One of the best ways to remove the oxide is by using a flux. Flux is essentially a very aggressive chemical that gets activated at the temperature slightly below the operating temperature of that process. And at that temperature, the flux reacts with the oxide, reduces the oxide, and converts it to parent metal. Now, once the oxide is gone, and as you raise the temperature, either the solder or the braze melts, and as it flows, now it has a clean surface to flow onto. So that's basically the job of the flux. The flux can be used in many ways. It can be used in form of a paste or a powder or a liquid, or you can actually dip parts in a molten flux, as I mentioned earlier. However, one of the biggest challenges with flux is a very strong chemical, often chlorides, fluorides, and sulfates, and so on. And you need to remove the residue post-processing. So there is a lot of post-processing involved to make sure that the flux does not remain there. So it needs to be washable, removable, and that can be a source of challenge, especially when you're trying to braze or solder into thin gaps where the flux residue can hide and create problems later on. So chemical fluxes are very common, but removing is a challenge, something you need to consider seriously. You might hear of something called no clean flux. So no clean flux means a flux which has very, very low level of chemicals and used in situations where you just need a very, very minimal amount of surface cleaning. But no clean does not mean there's no residue. No clean means there is still some residue, but for some applications, you're allowed to not clean it after the soldering process. So no clean flux is a unique situation where it's a very, very low level of cleaning. Ideally, you want to use a process where there is no flux. And that can be done. So you can create a reducing environment. A reducing environment is conditions on the surface of the component where the oxide actually reduces. What does that mean? That means the oxide releases the oxygen and converts to bare metal. So let's say you have stainless steel, which has chromium oxide on the surface. So you set up the conditions such that the chromium oxide breaks down, it releases the oxygen, and now you have pristine, clean, oxide-free surface on stainless steel for brazing. Now you can set up or create conditions for reducing environment in uh, inert gas ovens or vacuum ovens, or even in a hydrogen furnace where the hydrogen gas burns and creates a reducing environment. However, all of these processes only activate the oxides at a high enough temperature. So you cannot use these processes for soldering, the reducing environment processes for soldering. So that only works with brazing. So that's one of the benefits of going for brazing is you don't have to worry in some situations, you don't have to worry about the flux residue. Okay. All right, let's look at a summary of soldering and brazing. Soldering and brazing are popular joining techniques and which are widely used in almost all manufacturing industries, whether you are in medical devices, aerospace, automotive, everything. You can use soldering and brazing. There are many dimensions to soldering and brazing. As we reviewed in this presentation, you have to first select, make sure you are familiar with the base metal. Does that need any special treatment, such as, say, maybe have a plating on it? Then you have to select the right braze alloy or solder alloy. You have to select the right flux, which will be active, select the right temperature where this process could happen. And once you cool down, you also have to deal with cleaning the flux residue. So all of these have to work together for you to produce the desired result. Flux is used to remove oxides from the surface. So the main reason for flux is to reduce whatever little oxides there might be on the surface. Sometimes they're barely there, as in case of, say, copper. But sometimes these oxides are very aggressive, very difficult to remove, as in stainless steel. So more difficult to remove, you have to use stronger chemicals. Solder and braze alloys are often, not always, often a mixture of multiple metals. And the reason why they are mixtures is so that you can control not only the melting point, but you can also control the viscosity of the melt. So that will decide how small the gap these solder or braze alloys can go into by capillary action. If you want to fill gaps which are very thin, you need a very fluid solder or braze. If you want to fill gaps which are slightly bigger, you actually consciously need a little bit more viscous alloy. We also reviewed the different options for heating to make the solder bonds, and it can include ovens, lasers, induction, resistance, torches, many, many different things. And also for fluxes, as we saw, we can have chemical fluxes, we can have no clean flux, which just doesn't require too much cleaning. And we can also have a reducing environment acting as a flux. So this is the introduction. So keep in mind for soldering and brazing, there are three different elements: the solder alloy itself, the flux, and the design and the geometry, so that you can produce the desired result that is going to meet your specifications. Okay. Well, thank you for your time. This is just one of the videos that I have posted so far on the YouTube channel. You can subscribe to my YouTube channel by clicking the button to the bottom left. And if you go to the YouTube channel, there are multiple playlists, and playlists include laser welding, arc welding, resistance welding, welding metallurgy, other welding processes, and so on. And feel free to review those, and hopefully you'll subscribe and follow so that next time I post a video, it will directly come into your feed, and you can look at that one as well. Well, I want to thank you once again, and I hope you find this to be a useful and interesting video. And please subscribe, and please forward to others who might be interested in learning more about soldering, brazing, and welding. Thank you so much.